Thank you very much for waiting. Now we would like to resume the symposium and move on to the first session. Dr. Kazuo Nakashima will be the chairperson of this session. Dr. Nakashima, please come up to the stage.
Good afternoon, everyone. Welcome to session 1 of the JIRCAS International Symposium. I'm Kazuo Nakashima, director of the JIRCAS Food Program. This session focuses on the challenges of artisanal fisheries and aquaculture in the sustainable food systems. We have 3 distinguished speakers who will tackle such issues in the context of case studies in Japan, South Asia, particularly in the Philippines and Australia. Our first speaker is Dr. Tsutom MIYATA, Director of the Fisheries Division, JIRCAS. The title of his presentation is Issues of Artisanal Fisheries and Aquaculture in Sustainable Food Systems in Southeast Asia. So, Dr. MIYATA, please.
Thank you for Chair. So I would like to give you the introduction of my presentation at first. And okay, the expansion of intensive fisheries in pursuit of economic efficiency has further increased global greenhouse gas emissions, and has had a negative impact on the global food supply system, such as increased scale of the natural disasters and erosion of coastal area due to climate change. In left figure, you can see the total carbon dioxide emission from fishery increasing like this. And the reason why it's increasing carbon dioxide emission is motorization of fisheries. And the conversely, the catch amount of value have been declining like this because of the deterioration of the fisheries resources since 1919. And thus, so after 1919, the carbon dioxide per catch of industrial fishery and as well as a small-scale fishery increasing. However, both of artisanal fishery is generally no engine. That's why the emission of the carbon dioxide from the artisanal fishing is like this level. And anyway, our research target mainly artisanal and small-scale fishery and aquaculture. So I give you a case study of the artisanal fishing. We had conducted a fishing household survey in the village, where almost all fishers operate the artisanal fishing in this area. The place of the research site is the central Philippines, the northern part of the Panay Island. We targeted to the 3 municipalities. One is New Washington, second is Bataan, and the third is Altabas. The total number of the sampling was 464 fishing households. And the result showed that the average income of fishing household was about 64,000 Philippine pesos per year. And the criterion of a poor household by the Philippine government was 94,000 Philippine pesos per year. So, therefore, almost all fishing households in this survey area were poverty. And the major factor of the poverty in this village was overfishing. So you can see there is so many set nets in the fishing ground like this, and average catch per day continue to decline like this. So in 1970, the catch amount per day was 23 kilogram. In 1918, the catch amount per day was 10 kilogram. In 2000, the catch amount is only 5 kilogram. So that was the declining of the resources in this fishing ground. Well, so every fishers in village say that so fishery management is needed in our fishing ground. The definition of the fisheries management is a process that creates and enforces the rules that are needed to prevent overfishing and help overfish stock rebound. So thus, almost all respondents answered the very necessity to implement the fisheries management in their fishing ground in our question. So, however, we ask the officials the question as how many years and months can you tolerate the reduction in catch associated with the introduction of the fisheries management? The 62% of the respondents answered a few months or several months. And 67% of the respondents answered less than 3 years. Furthermore, 50% of the respondents answered, I don't know. So thus, virtually all respondents answered less than 3 years. The result shows that it is too short to recover the resources because it generally takes more than 3 years. So the participants indicate they could not tolerate the fishing management for a long time or long period of time because it would result in a lower fishing income in the present situation. Furthermore, we ask the fishers as next question as do you agree that there is no need to worry about the sea and fish? 55% of respondents answered worry about the sea and fish in the present situation. However, 45% respondents answered no need to worry about the fish, sea and fish. So thus, half of respondents believe the spontaneous recovery of fish resources. So this result indicates that fishers were divided. Therefore, it is difficult to implement bottom-up fisheries management and co-fisheries management. The management, participatory management by fishers themselves. It's also democratic management. So already I mentioned, anyway, the fish resources have declined, and almost all fishing households were poverty. And the measure for the improvement of these issues to implement the fisheries management with reducing the catch amount and to provide the alternative job and income to fishing household. And the third area is a famous oyster production area in the Philippines. The local intermediates distribute the oyster to big cities in the Philippines, such as Manila, and it's oyster road. And there are many diners and farm stand of oyster on the road. And furthermore, the area is famous as a prawn production area. So that's why we suggest the community-based marine protected area by oyster farm. It's for juvenile fish and juvenile prawn and juvenile sea cucumber. So the prawn is a very important species in this area, and you know the sea cucumber is a very expensive product in the world. So that's why oyster become a alternative income for fishing household and community. And we also suggest that the government, NGO and NPO support stock enhancement to release seedling of these species. And local university conduct research for sustainable production of them. Consequently, local fishers can sustainably catch adult size of them outside of oyster farm using their fishing gear. However, there is several remained research to implement this system. So that's why in fishery division of JIRCAS, we conducted the research and development with for target species is oyster aquaculture in Malaysia and in Myanmar, and so this is we conducted regarding intermediate seedling techniques in Philippines, and this is target species is a prawn, and anyway focus on the new technology of the seedling. And furthermore, in the past project, we had conducted integrated multi-trophic aquaculture (IMTA) research until 2020. So that's why I strongly hope the community-based multi-trophic aquaculture research, aquaculture with a marine protected area system is implemented at the research site and other site in near future. So that was my presentation. Thank you very much for your attention.
Thank you very much, Dr. Miyata. The next presentation will be given by Dr. Kazutaka SAKIYAMA, the Director of the Production Engineering Division, Fisheries Technology Institute, Japan Fisheries Research and Education Agency. Dr. SAKIYAMA will talk on issues of sustainable aquaculture seedlings in Japan. Dr. SAKIYAMA, please.
皆さんこんにちは。水産研究教育校の崎山です。私からは日本における魚介類の種苗生産技術について話をさせていただきます。それでは通訳さんよろしくお願いします。今回ここではブリやサーモンなどのメジャーな魚介類養殖魚ではなくて新しい魚介類の種苗生産について話をします。この図は日本の列島を示しています。日本の海洋環境について説明します。この図は、南北に長い日本列島は亜寒帯から温帯、亜熱帯までさまざまな気候が存在します。また北の方は寒流が、南の方は暖流が流れ、それと複雑な地形を有していますので、さまざまな魚介類が生息するとそういう海域となっています。日本人はそれぞれの海域に生息するたくさんの魚類の漁獲して食料として使用してきました。現在日本近海には3000種類以上の魚類が生息しています。そのうち約500種類が食用とされています。この他にも甲殻類や貝類、海藻などたくさんの種類が生息してそれを食料として利用しています。これらの魚介類の安定供給は地域の発展のために極めて重要です。そのため漁業だけではなく養殖によって安定供給しようという試みがなされています。養殖にはたくさんの魚類、稚魚が必要です。日本の代表的な養殖魚であるブリやウナギでは天然の種苗が使われていますが、天然種苗は年によって漁獲ビ数が大きく変動します。また取りすぎると天然資源に影響を及ぼします。そのため養殖を持続的に実施するためには人の手でたくさんの稚魚を育てなければなりません。たくさんの種類の稚魚を育てる技術を開発するには 多大な労力と時間を必要とします。しかし日本では幸いなことにサイバー漁業で培った種苗生産技術が存在しますので、この技術を活用して養殖種苗を生産することができます。この図はサイバー漁業の工程を示したものです。赤枠が種苗を育てる工程になります。この中で種苗を育てた後、海や川に放流して大きく成長したものを漁獲します。このうち赤枠の種苗を育てる工程、この部分は養殖用の種苗を育てるところと類似しています。日本ではこの工程の中でたくさんの種類の種苗生産技術を開発してきました。現在までに日本で種苗生産が可能になった種類は、魚類が73種、甲殻類23種、貝類38種、その他ウニ、ナマコ等が16種で合計150種に上ります。これらすべての魚類が養殖対象になるわけではありませんが、この中には養殖用種苗として利用されているものもあります。有名なものではマダイやヒラメ、車エビが該当します。近年ではブリやクロマグロの種苗生産も該当します。魚介類の種苗生産技術は魚類、甲殻類、貝類、ウニ、ナマコのそれぞれでスタンダードな方法が開発されてきました。しかし魚種によっては工夫が必要ですし、さらに効率的に生産するためには新たな技術の導入が必要です。特に新しい魚類については既存の技術だけではうまく生産することができません。新たな魚種の種苗生産技術の開発では、種苗生産技術の開発に重要なことを説明します。一つは対象種の幼生の行動や生態をよく観察して、その対象種に適した飼育技術を考案することです。もう一つは他魚種で開発された技術、あるいは水産だけではなく農業や工学の分野で開発された技術を積極に導入して、さらに改良を加えることです。今回ここでは詳細な幼生観察により飼育に成功した事例として、マダコとタイラギという二枚貝を紹介します。また新しい技術を導入した事例としてホシガレイとヒジキを紹介します。他の魚についてもいろんな事例があるんですけど、今回は時間の都合でこの4種にさせていただきます。まずマダコです。マダコの消費量、これは世界的に増加していますが、資源状態はかなり厳しい状態となっています。そのため人工種苗の生産技術が求められてきましたが、長年どの国もどこでも成功しませんでした。その理由としましては、マダコ幼生の大量飼育に適した餌、生きた餌しか食べませんので、その餌の確保が難しかったこと、それからマダコの幼生自体がどういう生態を持っているかということが全く分からなかったためです。そのような中、水産研究教育機構ではマダコ幼生の飼育技術の開発に取り組み、大量生産技術に成功しました。この中でまず行ったのは水槽内でのマダコ幼生の行動観察です。単純ですけども、これが非常に重要です。その結果、幼生は餌を捕まえると水槽の底に沈んでしまって、その時点で餌を離してしまうということが分かりました。そこでミギズのような飼育装置を開発して、飼育水槽底面に海水を吹きつけて、そこから上の方に向かう流れを作ることでマダコ幼生が沈むのを防止しました。またマダコ幼生の餌としてカニの幼生が適していることが分かってきましたので、それを大量生産するために栽培漁業で開発されたカニの種苗生産技術、これを活用して大量のカニの幼生を確保することができました。この方法によって冬から着底までの幼生の生産率が飛躍的に向上し、90% 以上に達しました。このチダコを使って、さらに養殖試験を行ったところ、この左の方の写真になるんですけども、約10ヶ月で1キロに成長する非常に成長の早いことが分かりました。ただしこれは簡単に養殖できるものではなくて、マダコの中では一番大きな問題、共食いが養殖の障害となっています。現在チダコの生産が可能になりましたので、現在は共食いについての研究を続けているところです。 次に平らぎの種苗生産技術に紹介します。牡蠣やアサリ等の種苗生産技術はすでに開発されていますが、この方法は平らぎには全く通用しません。平らぎ幼生の飼育が難しいのは、幼生同士がくっついたり、あるいは水面に浮いて固まって死んでしまうためです。そこで水槽内に水流を発生させる方法と、水面に浮いた幼生の塊を分離させて沈めるためにシャワーを吹きつける方法を開発しました。これは左の方に図になります。この方法によって、ある程度稚貝の生産が可能になったんですけども、この方法はポンプに吸い込まれた幼生が傷つくという問題が出てきました。ただし、この方法についても技術開発を進めまして、現在一度に数百万個体の稚貝を生産することができるようになってきました。ただしまだまだ技術の改良は必要です。先ほど紹介したマダコと平らぎは種苗生産が非常に難しい種類でしたが、詳細な生態観察と飼育担当者の創意工夫により生産技術が大幅に進歩した素晴らしい事例だと考えています。続きまして、新たな技術導入により生産に成功した事例について説明します。最初にホシガレイの話をします。ホシガレイは非常に高級な魚類で、冷水性の魚類としては比較的成長が早く特徴があります。近年いろんな方面で LED 技術を利用したさまざまな試みが行われています。そこで今回もいろんな照明で生物を飼育する、このホシガレイを飼育するということを試みました。右の図は5つの色の照明と自然光でホシガレイを飼育した時の体重の変化を示しています。横軸は飼育回数日数です。実験開始40日目、60日目の体重を見ると、緑色の光で成長が優れていることが分かります。この実験に関連してさまざまな調査を行った結果、緑色の光で成長が早くなった理由としまして、ホシガレイの食欲が増進したということが分かりました。現在この結果を活用して、漁協等と協力してホシガレイの陸上養殖の実証試験に取り組んでいるところです。次に海藻のひじきの種苗生産技術について紹介します。ひじきは日本の代表的な海藻ですが、その多くを海外から輸入しています。その安定供給のために国内で養殖や塩害期の増殖が望まれています。そのためにはひじきの種苗生産が必要となってきますが、その中で大きな問題となるのが、ひじきと同時に雑海藻、アオサなどが繁茂することが問題となっています。この問題を解決するために、ひじきの成長に影響なくてアオサの成長を阻害する照明食について実験を行いました。またもう一つ面白い方法として、アオサに魚を食べさせる方法についても実験を行いました。右がその結果です。照明の色とひじきの成長を見ると、緑色の光でひじきの成長が優れていることが分かりました。一方、アオサの緑の光で繁茂が抑制されることが分かりました。また、ある程度時間が経つと、アオサが繁茂してきます。LED を照明していても繁茂してきます。そこでこの繁茂した状態、真ん中の写真の状態の時にメジナを投入します。そうするとメジナはアオサだけを食べて、ひじきだけ残るというふうな結果になりました。なので、初期は LED 照明で、途中でメジナを投入すると、非常に簡単な方法というか、やりやすい方法でひじきを育てることができるようになりました。繰り返しになりますが、魚介類の種苗生産技術開発のためには、対象種の行動や生態観察が必要です。積極的に新しい技術を導入して改良することが重要です。またこの飼育技術、これは生き物の生態とか生理、それを調べる方法としても有効ですし、天然ではわからないこと、それを調べる方法としても有効です。この3者が結びつき合って、新しい種苗生産技術の開発もできます。日本各地にはたくさんの魚介類が存在しています。いろいろな魚介類の種苗生産技術が開発されることによって、日本のそれぞれの漁村で特徴のある魅力的な魚介が生産され、安定的に供給されるようになります。 安定供給されることによって、国内外の観光客への提供とか観光利用も可能になります。これにより各地の漁業者の収入の増加と安定化、さらに地域活性化が進むことを期待しています。左上に海鮮丼というものがあります。日本全国でどこに行っても同じ海鮮丼が食べても面白くありません。私の夢は日本各地を回って写真にあるようなさまざまな種類の海鮮丼、おいしい食べ物を食べて地酒を楽しむことなので、いろいろな種類の種苗生産技術、いろんな種類の魚介類の種苗生産技術、それが開発されることを望んでいます。ご清聴ありがとうございました。
Thank you very much, Dr. Sakiyama. Let me now introduce our last speaker in this session, Dr. Jeffrey T. Wright, Associate Professor of the Institute for Marine and Antarctic Studies, the University of Tasmania, Australia. The title of his presentation is Potential of Seaweed Utilization for Greenhouse Gas Emissions Reduction. So, Dr. Wright, please.
Great. Thank you very much. It's nice to be here, and I'm very grateful for the invitation to give this talk to you today. And specifically what I'm going to talk about is the way in which the seaweed you can see on the bottom right can be used as a feed supplement to reduce methane production in ruminants, in cows and sheep and goats. So we know that methane emissions, methane is the second largest contributor to global warming after carbon dioxide. We know that methane emissions are much greater than they were pre-industrial times. We know that methane continues to increase at record levels. So the bottom figure there is just for the last 40 years. And although methane is much less abundant than carbon dioxide, it absorbs more energy per molecule and has a shorter lifespan, and consequently it has a global warming potential much higher than that of carbon dioxide. And for these reasons, the high global warming potential of methane suggests that rapidly reducing methane may be one way to, reducing methane one way to rapidly mitigate some some of the effects of global warming. So, of the total anthropogenic methane budget, shown in orange on this slide, a large proportion, around about 56%, comes from agriculture and waste. And of that 56%, a large part of that is due to enteric fermentation and manure from ruminants. And this occurs because methane is emitted from cows and sheep and goats during digestion. This happens when the microbes in the gut of the animal decompose and ferment the plant material, and methane is released as burps. So, because of the large contribution of ruminants to the global anthropogenic methane budget, a range of feed supplements have been trialled to reduce enteric methane, and of the supplements that have been trialled, seaweed appears to be the most promising, and in particular one species of seaweed. The figure you can see here shows the experiments that were done in the lab. So these were done in test tubes in the lab, so they're in vitro experiments where small amounts of 24 different species of seaweed were added to rumen fluid during fermentation, and methane was measured. And of all the 24 species tested, Asparagopsis reduced methane production by 99%. So that's in a lab. Some follow-up experiments have looked at what happens with animals, and that was first tested in an experiment done in stalls using respiration chambers. In this experiment, different amounts of Asparagopsis was added to the diet of cattle in these stalls, and when there was the highest concentration of Asparagopsis in the diet, which was 0.2% of dry weight, so it's not very much, for 0.2% of dry weight, there was a 98% reduction in methane produced, so still a really strong effect. In a more realistic situation of animals wandering around in the paddock, some follow-up experiments have been done that used these green feed systems where animals are allowed to forage, but then they're attracted to these systems because there's dry food in those systems, and when they're feeding on the dry food, the amount of methane they're breathing out can be determined. And the experiments that have been done using these systems have also shown really strong effects of a small amount of Asparagopsis in the diet in reducing methane production. So there are 2 Asparagopsis species that are currently being cultivated with, for intended use as feed supplements. Asparagopsis taxiformis, which is a warm, temperate to tropical species, and Asparagopsis amata, which is a temperate species. Both species have 2 free-living stages in their life cycle. In the photos here, you can see what's called the gametophyte stage, and those plants are about that tall. And they have a second free-living stage, which is called a tetrasporophyte, which are these little sort of fluffy balls that are about that big. Reproduction occurs sexually by spores, and reproduction can also occur asexually via fragmentations, where where pieces of the plant break and can float away and form new individuals. One difference between the species that's important in terms of the fragmentation of gametophytes is that the Asparagopsis amata gametophytes have barbs on these little barbs that grow out of the plants, and when fragments with these barbs are created and float away, the barbs allow the fragments to hook onto substrata such as other seaweed, but in cultivation can hook onto ropes as well. Both the species produce bioactive compounds. These bioactive compounds inhibit enzymes that produce methane during digestion, so that's the mechanism by which the effect occurs. Bromoform, the structure of which you can see here, is the most abundant of those compounds, and the compounds are stored in, you can see the little dark cells in the photo up on the top right. The compounds are stored in those gland cells. So in a number of companies globally are now growing Asparagopsis for use as a feed supplement. All of these companies have started since 2018, so it's all very recent. And several of these companies are now making good progress and are starting to sell Asparagopsis. I work quite closely to the company Sea Forest, which you can see in the bottom right. They're based in Tasmania, where I'm based as well. So because Asparagopsis has these 2 morphologically distinct stages, there are 2 different strategies for cultivation. The tetrasporophytes, the small fluffy balls, are grown in land-based systems. The 3 photos here just show 3 different tank setups in the labs for 3 of the different companies that are cultivating the tetrasporophytes, and 2 of those are for Asparagopsis taxiformis, and 1 of those is for Asparagopsis amata. The other approach is sea-based cultivation of gametophytes, and this is essentially where the gametophytes are attached to rope, and those ropes are put out in the sea and they're allowed to grow before being harvested. So for tetrasporophytes, the land-based cultivation starts with seeding of either spores or fragments of the tetrasporophytes. We end up with lots of small baby tetrasporophytes. These are then placed into flasks in a hatchery. So these are small flasks. They're put into the flasks at a certain density. They're allowed to build up biomass in the small flasks, which are 5 to 10 litres or thereabouts, before being placed into larger tanks for grow out. The photo that's shown here is a 17,000 litre tank, an outdoor tank, but as you saw in one of the previous photos, that their indoor tanks are commonly used as well. Once they grow out to a certain biomass, they're harvested, and then the processing has to occur. The compounds are quite volatile, so the processing needs to occur to make sure that the compounds are retained in the biomass, and this can be done either via freeze drying, or by placing the tissue in oil and the oil extracts the compounds. And both of those strategies are effective at retaining the compounds in the product, and then once they're in that form, that can then be fed to the livestock. A small amount of the harvest is kept as the seed stock for fragments for the next round of production. Sea-based cultivation of the gametophytes also starts with the production of seed stock from either spores or fragments. The spores are settled onto string in the lab and then grown to a certain size before they're outplanted. The fragments are created, where the fragments of Asparagopsis amata have the barbs that will enable them to hook onto the rope for the outplanting. And then they're taken out to the marine farm. The attachment or the method for the spore-based production is similar to how kelp is produced in a sea-based system, whereby the settlement onto string occurs in a lab. Then those strings with the baby algae are then transferred out into the ocean and they're wrapped around a larger rope for them to grow. They're allowed to grow on the ocean farm to a certain size before harvest occurs, and once they're harvested, they're processed and in the same way and fed to cows, just as the tetrasporophytes. And similarly, a small amount of the gametophytes are kept as for the propagules for the next round of seeding based on fragmentation. So currently, Sea Forest, the company that I work with in Tasmania, are focused on gametophyte cultivation. They currently have a 1,500 hectare lease for seed-based cultivation of gametophytes, and they're working on about an 8 to 10 week production cycle from outplanting to harvest. And they're partnering with a large dairy company and also a large beef producer in Australia. So given the cultivation of Asparagopsis is at such an early stage, there are obviously lots of opportunities here and lots of challenges that are being worked through by all the companies. As for any aquaculture species, closing the life cycle is fundamental for production, and some of the companies, the information on their websites indicate they've closed the life cycle, but none of that information is really publicly available. The industry is in its infancy, so there can be lots of improvements to the whole method of production, from seedling, hatchery and production. There's been very little strain selection or selective breeding thus far, and so being able to enhance production with high-performing strains is an avenue, is a real opportunity. There are limits to the access to the ocean for farming, and certainly in Australia there are only certain places and where you're able to farm, have aquaculture farms, including seaweed farms. So that's an issue as well. And then finally, it's probably important to think about the biomass that's required here to supply the global industry. One estimate of the amount of Asparagopsis to supply 100% of the beef cattle in Australia, which is 1.1 million cattle, so these are just the feedlot cattle, is 29,000 tonnes dry weight, which is around about 200 to 250,000 tonnes wet weight. So the amount of Asparagopsis to supply the global market is large. And certainly the companies who are producing Asparagopsis are looking at upscaling their production. On the left is one of the properties that Sea Forest have, which has 660 of these large 17,500 litre ponds that could potentially be used for land-based cultivation of tetrasporophytes. Okay, just a few take-home messages. Methane is a significant contributor to global warming. Enteric methane produced by ruminants contributes about 30% of anthropogenic methane emissions. Feeding ruminants small amounts of Asparagopsis reduces methane emissions significantly by somewhere between 65 and 98%, the science tells us. Mass cultivation of Asparagopsis is feasible, but it's very much in its infancy, and consequently there are lots of opportunities to optimise production of Asparagopsis to meet the demand both globally but also nationally within lots of different countries. Thank you.
So thank you very much, Dr. Wright. Now the floor is open for discussion, but unfortunately, because we are more than 10 minutes behind the schedule, I would like to take one or two questions to any of our speakers from the audience. Are there any questions, comments from the floor? No questions or comments? So if not, I would like to address my questions to Dr. Wright. Dr. Wright, yeah. Thank you for your interesting presentation. So I'm very excited about the use of asparagopsis to reduce greenhouse gas emissions. But what is the profitability of using seaweed as livestock feed? Yeah, that's my question.
Thanks for the question. It's a very good question because any feed supplement is a cost to the livestock farmers. I think the things that are probably important to consider are, I didn't talk about this, but there is some evidence that because the asparagopsis is stopping methane being produced, some of the carbon that would be emitted in methane can be reassimilated by the animals, and so they can actually enhance productivity. So that's one potential benefit. A second one is, and this isn't in place in all countries, is that there can be carbon credits claimed by the producers. So if there's a carbon credit system in place in that country, then potentially the producers could claim credits for reducing the amount of carbon that's getting emitted, and they could benefit that way. And the third thing, again, I'm not sure if this is something that will be in place everywhere in the world, but in some parts of the world, and Australia is probably one of these, there is a certain proportion of the population of people that, and it's probably quite a small proportion, but who are happy to pay a little bit more for food that they know might be carbon neutral. And so there could be, I think there are probably three sources that we could think about.
Oh, thank you very much, Dr. Wright. So I think somebody may have the question for the speakers. Please ask directly to the speakers during the break time or after the session. So I think it's time for us to close this session. So in this session, we learned about the challenges facing artisanal fisheries and aquaculture towards achieving sustainable food systems in Southeast Asia and Japan, and the potential of using the seaweed to reduce greenhouse gas emissions and combat climate change. I'd like to close this session by thanking all the presenters for their illuminating presentations and discussion. Finally, please give a big round of the applause to the presenters. So thank you very much.
Thank you very much to the speakers and chair of the first session. Dr. Nakashima, please return to your seat. Thank you.